Hi guys, in this video we are going to learn how to find the resultant impedance of a series circuit as well as parallel circuit. As you already knew, as we have already learnt about the impedance, we can directly tell the impedance is going to have two main parts, which is known as resistance. The real part is known as resistance and the imaginary part is known as reactance part. So the impedance is going to be the addition of these two, resistance plus reactance. So we already knew that. Also, if you are new to this expert tutor channel, please consider subscribing. Also, if you have any doubts or if you like to learn any topics related to electrical engineering fundamentals, I have given the link in the description, so you can always watch them. So when we are considering about the series combination, first of all we need to understand what's going to happen over there. Actually, we have already learned that when there are resistance in the series circuit, we can directly tell the total resistance would be the sum of those resistance which are in the series. Likewise, here we are going to tell the Z would be equals to the Z resultant would be equal to, let's say, the Z1, Z2, Z3. There are now n times of impedance in a series circuit. The resultant would be Z1 plus Z2 plus Z3 up to n. This is likely to the resistance, total resistance. When we are considering about the total resistance in a series circuit, we are going to add up them. Likewise, when we are considering about the parallel circuit, let's say the impedance of a parallel circuit we can tell this directly. It's going to similar to the resistance parallel circuit. When we are considering about the resistance, we already knew that the 1 over R equivalent would be equals to 1 over R1 plus 1 over R2 plus 1 over R to the power, Rn. Likewise, here we are going to tell like that one. Let's say the 1 over Z equivalent would be equals to 1 over Z1 plus 1 over Z2 up to 1 over Zn. Actually, we already knew this 1 over Z is known as admittance. So in the other sense, we can tell, if we write like this in the admittance form, we can tell it's going to be Y equivalent would be equal to Y1 plus Y2 up to Yn. So in two forms you can directly tell like this one. So the thing over here is, some might wonder how we are getting this type of equation for a series circuit, why we are adding these things, and for the parallel circuit, why are we adding the admittance? So the answer for that question is, let's consider a series circuit which is having impedances. Let's say this is Z1, Z2 and Z. Actually, we knew that when we are considering about this one, we can directly tell the I would be equal to all these three components. As they are in the series, when one component received the I current, these two components also going to have this I component, the same current. So from that, we are going to draw an equivalent circuit for this. Let's say there is an equivalent impedance for these three. If I draw that one, we can directly tell the I is going to be same for this Z equivalent to. The reason behind this is, when we are considering about the total impedance, the resultant of these three also, it's going to have the same current. So we can tell it's going to be the I again. So from that, let's say if we consider about the voltage differences, let's say this is V1 and this is V2 and this V3. If we are considering about the voltage differences, we can tell that this voltage difference would be equals to these three voltage difference. That's the idea behind these equations. So we are going to use this part to get this one, as well as when we use the same idea for the parallel circuit, we can directly tell the voltage between that component in the parallel circuit is going to be the same. From that, we can total up the current for each circuit and add it up, and after that we can get an equation for like this one. So I'm going to do for the only for that series circuit, you can do similar method and get the answer for this one. So when we are considering about this, I have already mentioned the V is equal to V1 plus V2 plus V3. Actually, we knew that when there is a current high, the voltage difference, we already knew that V, we can directly write this V is equal to I into the impedance. V is equals to IZ, that's the equation. So we can directly tell it's going to be IZ equivalent. So this is the main part. Likewise, you can directly tell when you are considering about the V1, we can use the V is equals to IZ equation. For this part, we will be getting V1 is equal to I into Z1. As the current is same, we can directly write it's going to be I into Z1. Likewise, for this one, we can directly write I into Z2. For V3, we can directly write I into Z3. If I cut down the I as they are similar, I'm going to get the Z equivalence would be equal to Z1 plus Z2 plus Z3. So this is a method to derive these two equations. You can use these two equations directly if they have given either series or parallel. Hope this video would be useful for you. If you have any doubts, please comment it below. See you in another video. Thank you.